everyone. In this section, we're going to discuss two attribute charts, the P chart and the C chart. The P chart is used to control and minimize the proportion defectives in a process, while the C chart is used to control and minimize the total number of defects produced in a process. We want to be able to understand when to use P and C charts for monitoring and controlling attribute characteristics. We want you to be able to calculate the 3 sigma control limits for P and C charts and to construct and interpret the data in P and C charts. The P chart is an attribute control chart. And it's used with count data arising from inspection by attributes. The P chart is also known as the fraction defective or fraction nonconforming chart because it's used to monitor and control the fraction produced in a process that is defective or nonconforming. And just a note from our author, the term defective was the original name used in the SPC literature for anything that did not meet the specified requirements. And so the P chart was known as, just said, as the fraction defective chart. But nowadays we talk more about non-conforming. This is more common because since about 1980, you started to get liability suits and this type of thing became more common. So the idea of being defective was very negative, had a very negative connotation. So almost as though the unit would be unsafe or dangerous. So now we use the term non-conforming. It simply means that the unit in question is not meeting the chosen specifications. And here we might change a little bit, sometimes switch the terms, but basically I'm going to stick to the term defective so it's easy to read, and also it has, just keep in mind that defective or non-conforming, we've been talking about defective, so we're going to stick to that here. Now the P chart is typically used when you have a very large continuous production that has some defectives produced and where the proportion of defectives should be monitored or reduced to a minimum, even to 0. So the P chart, it requires usually a large sample size, generally something n greater than 20. The method consists then of taking a sample of size n at a regular time interval. You're going to inspect the sample and count the number of defective units in the sample. And this number of defective units is going to be equal to a random variable d, which is then our binomially distributed random variable. So then the proportion of defectives in each sample is computed then and we call this little pi for the ith sample. And we plot it in a control chart with control limits drawn on the chart. So just a couple terms here. P is going to be the proportion defective in the population being controlled. So this is a population parameter, P, whereas big P is the statistic that represents the proportion defective in a sample. And we're going to call little pi is the proportion defective in any particular, the ith sample. So the value of the statistic P in the ith sample. And P bar is going to be the average of our PIs. So we calculate that here. P bar is going to be the sum from 1 to k, where k is the number of units for completing the limit. So the number of units in each sample that we're using, the number of samples that we're using, pi divided by k. And we'll look at that in an example in a minute. So we have, for example, 50 samples. We'll take the pi for each of the 50 samples and then divide by 50. So The control limits are calculated using these formulas. The UCL, the upper control limit, is going to be this P bar value, the average proportion in roughly about 25 samples, times 3, times the square root of P bar, times 1 minus P bar over N, where N is the size then of each sample. So again, we said N should be fairly large, about 20, over 20. And we're going to use about 25 samples then to get this P bar then. Now, we're not showing the derivation of these formulas. By the way, the center line is going to be just the P bar, and the LCL is going to be the same thing with a minus sign. We're not showing the derivations of these. This is in our textbook if you want to look more further. But what we're interested in here is that this P, this statistic there, is related to the random variable D, the number of defective units in the samples, and that is binomially distributed. So what we've got here are the 3 sigma limits, where the sigma, here's our plus or minus 3 sigma limits, sigma P, again, you don't need to know more than this, is standing for the standard deviation of the statistic P. But for our purposes here, the upper spec limit and the lower spec limit for the control charts, you will take the data, you'll use these 3 sigma equations, and you can calculate and plot the control limits. So, proportion defectives, as we said, is also the same thing as proportion non-conforming. Okay, let's look at then an example. Samples of 50 screws produced by an automatic lathe were taken every half an hour, and the screws were then gauged for length, diameter of head, and the slot position, and were visually checked for finish. The number of rejected in each sample was then recorded, and the fraction defectives then in each sample is calculated as PI, which we're seeing here in this bottom row. So here's our subgroup. We have subgroup 1, subgroup 2, subgroup 3, sample 1, sample 2, sample 3. We have 25 samples that we're using. The size of each sample or subgroup is 50. And so, for example, if we look at, for example, sample 3 here, actually, let's look at sample number 5 here. We have sample number 5 has 3 defectives from 50 is equal to 0.06. So this is P sub 5, the proportion defective in sample 5. And so likewise for sample 12, we have 1 defective out of 50, so the P12 is going to be this 0.02. Now, if we calculate the average of all of these, the average P would be the sum of all these PIs over 25, and we get 0.027 as our average, our P bar. Now, we can use this data and then calculate our control limits. We have the P bar, and we have, so here we go, the P bar, plus or minus 3. This is going to be P bar, and then we have times 1 minus P bar. And here we have the N value that we used in every sample, so the sample size. And if we can't calculate the upper spec limit, we get 0.096. We already had the P bar was equal to the 0.027, and here with a minus sign we get minus 0.042. Now, we're constructing control limits for the count of defects. We can't have a negative number. So if it's negative for LCL, then it's rounded off to 0. Okay, now let's look at a plot of this data. So here's the data here at the top again for the 25 different samples with n equals 50 for each sample. And here we have the, the UCL here is equal to 0.096, and the LCL is equal to 0. Why is that? Oh, excuse me. The LCL here is equal to 0. And here is our center line is equal to 0.027. So there's the center line. There's the lower control limit. All right. So what we see, though, is that our process is not in control. We see there are 3 points. Sample 3, 4, and 6, 3, 4, and 6, all have PIs over 0.96. So what do? Well, just as before with the X-bar and R charts, the action is necessary to find out why these PI values are outside the limits. And in this particular case, the reason that we had several large PI values at the beginning of this process, because the process was going through a setup. And when the setup was complete, then the PIs settled down here. You can see at a lower level. So that was, we don't see this in this example, but that's what happened when these out of control values were investigated. So as we said before, we've got to find these causes and then eliminate them. So done that. And when the values are known and there's assurance that this cause, a setup time, for example, would not reoccur, then the PI values that are outside the limits can be removed from the data and you can calculate new limits. So the samples from 3, 4, and 6, then the values are removed. And if you take the remaining 22, so we had 25 subgroups, now we've only 22, we end up with a new P bar value and, again, new control limits. Center line 0.016, UCL 0.07, and LCL 0. Now this is lower than before. Before it was 0.096, but now we have the data. We've removed those outliers, the out of control points. So if we plot this again, so here we have the UCL equal to 0.7 here. LCL is equal to 0, and here we have the P bar at 0.016, and you see that all the data lies within these limits. So we can then say, all right, these limits are fine. We will use these to control our process, and then if we see some assignable cause or some kind of trend, then we would notice that with help of these control limits.